Hello students, welcome back once again to the JCE Connect, and we were discussing about the design of shear strength of pre-stressed concrete beam. So in the last session we had solved one problem to determine the shear capacity of pre-stressed concrete beam, and we also checked the shear capacity of the beam or the behavior of pre-stressed concrete beam will changes due to presence of pre-stress or without pre-stress, that is when the tendons are prodded with concrete beam and without tendons, that is with pre-stressing and without pre-stressing. And we ultimately got to know that, or we had concluded that a beam with a pre-stressing force will increase the shear capacity of the beam. Okay. So in the same today we are going to solve again the similar type of problems to check the shear capacity of the beam. Okay. So in today's session we will solve the problems. Okay. So it is a similar problem. The statement of the problem is also same as what you have solved in previous session. So I have not written the statement of the problem once again. I have written the given data here. So I will go through the given data first. Okay. So it is given as the span of the beam is 10 meter and the cross section of beam is 120 mm by 300 mm, 120 mm width and 300 mm deep. The pre-stressing force in the cable is 180 kN and the load over the beam is 5 kN per meter, which includes its self-weight also. So we don't have to calculate self-weight and add it into this. So the 5 kN per meter, it includes the self-weight also. Then the cable is parabolic. So this is a change here, and which is important again. Okay. The cable is parabolic with eccentricity 0 at support and 100 mm at midspan. So the cable is parabolic here with the eccentricity at support is 0 and at midspan it is 100 mm. Okay. So we can see the detailed in this sketch. So we have the beam of span 10 meter which carries a load of 5 kN per meter, and the size of the beam is 120 mm wide and 300 mm deep. And we have the cable profile is parabolic. Here we can see the cable profile is parabolic with the eccentricity at support is 0 and at midspan it is 100 mm. So this is as per the given details. Okay. So after that, as we know that the cable profile is parabolic, so P in the cable is, the pre-stressing force in the cable is 180 kN. So we are going to deal with the shear. Okay. We are going to deal with shear, so that it may be horizontal or vertical force. Shear is a horizontal force in the cable or vertical force in the cable. So for cable profile parabolic, we have to find out its component, that is horizontal component and vertical component. So with respect to theta, the horizontal axis. Okay. So I can see here PV is equal to P sin theta, the vertical component of pre-stressing force. PV is equal to P sin theta. So nothing but PV is equal to P theta, since theta is very small. So we are taking sine, we are not considering sine. So that's why PV is equal to P theta. Okay, and even the pH is P cos theta. So we are ignoring cos theta. So pH is equal to P, which is nothing but the effective pre-stressing force in the cable. Okay, so that is that since the value of theta is very small here, in the problem I can elaborate more effectively why we are not considering sin theta, or why we are not sin, or here why we are not considering cos theta, because the value of theta is very small in the cable profile. Okay, so that's why. So we have to consider PV is equal to P theta and pH is equal to P. So that is nothing but the pre-stressing force in the cable. Okay, so this is regarding the components, vertical component and horizontal component. Okay, understood. So next we have, if we get cable profile like this, if we get cable profile like this, so we have first the parabolic cable profile, then next is sloped cable profile with eccentricity E at midspan. Okay, so that time we have to use theta is equal to 4E by L for parabolic cable, and for sloped we have to use theta is equal to 2E by L, 2E by L. So in this case, if I calculate the theta, so that is 4, E is 100 and L is 10,000, 4E by L. Okay. Okay. So if we calculate theta is equal to 4E by L, so we are getting the value of T 0.04. So we can see the value of theta is very less. Okay. So that's why we are not considering. If I again multiply sine of, so we are getting very less answer, that is I can show you 0.00069. So that's why we can see we are getting 0.00069. So that's why we are ignoring sine and cos. Okay, so we are considering only P theta. In horizontal, pH is equal to P. Okay, so if cable profile is sloped, so we have to take 2E by L. So if profile 4E by L if for parabolic. Okay, understood. So now we will go for the solution. Okay, so first is shear stress. Tau V is equal to, it is V A Y bar upon I B. Is a basic formula for shear stress, but for rectangular cross section, as we have discussed already, so we will get tau V is equal to 1.5 times V upon BD, 1.5 times V upon BD. So we have to find out the shear force. So therefore the shear force, that is V in the beam, shear force V in the beam. Okay, so here, as you know, our cable profile is parabolic, as I told you. So we have to find out the horizontal component and the vertical component. Vertical component is P theta. Okay, and also we have the beam is carrying a load of 5 kilonewton per meter. This will generate a vertical force of WL by 2 and WL by 2. Okay, so here if I consider the force or the component of P, vertical component P, that is P theta acting downward, and the reaction developed because of the force 5 kilonewton per meter which acting upwards. So the summation of these two will be the design shear force in the beam. Okay, so we can see here these two forces, this force is acting downward, this force is acting upward. So the ultimately the shear force is summation of these two forces. Okay, so therefore V is equal to summation of vertical forces. We know that the shear force is nothing but the summation of all the vertical forces. So at support we have, so that is first due to load, so that is WL by 2, which is acting upward, so positive, and this is acting downward, so this is P theta. So this is the shear, the maximum shear developed in the beam. So we will calculate that. So here we have, I will just note down, phi u into L is 10 meter, W is 2, so divided by 2, minus P into theta, so that is theta is 4E by L. Okay, 4E by L. Okay, so that is nothing but, sorry, this is nothing but PV. So this is nothing but PV. What the shear force, the vertical shear force due to load minus the downward force due to the component of pre-stressing force. Okay, so that is WL by 2 minus PV. Understood? So then, so we have WL by 2 into P into theta, the PV is P theta. So P theta is 4 into 4E by L. Okay. So here, so we will calculate PV first. So therefore PV is equal to P into 4E by L. So P is 180 into 10 raised to 3 into 4 into E is 100 by L is 10,000. So we will get this as 7200 Newton. Let me check. So yes, it is correct, 7200 Newton. And WL by 2 is, the value of WL by 2 is, W is 5 into 10 raised to 3 to make it in Newton. Okay, sorry, I think it is not visible. So 5 into L by 2, so 5 L is 10 meter divided by 2, so it is 25 kilonewton or 25 into 10 raised to 3 Newton. Okay, so therefore the shear is WL by 2 minus PV. So WL by 2 is 25 into 10 raised to 3 minus 72,000. Okay, 7,200. So we get the design shear is 17.8 into 10 raised to 3 Newton or 17.8 kilonewton. This is the maximum shear. Okay, let me check. So 25 yes, it is 17.8 kilonewton. Understood? So therefore shear stress tau V is equal to 1.5 times V, so that is 17.8 into 10 raised to 3 divided by BD. So B is 120 and D is 300. So we will get this shear stress as 0.741 Newton per mm square. The shear stress developed in the concrete is, this much shear stress is developed in the concrete. Okay, so beam has to carry this much of shear stress. Okay, so that is 0.741 Newton per mm square. So next is principal stresses. Next is principal stresses. So for that, first is direct stress Fx that is P by A. P is 180 into 10 to 3. Area is 120 into 300. P by A, that is we get 5 Newton per mm square, and Fy is equal to 0 because we are not providing any vertical pre-stressing system, we are providing only horizontal pre-stressing system. Okay, that is Fy is 0. So therefore F is equal to Fx plus Fy divided by 2 plus or minus half of square root of Fx minus Fy square plus 4 tau v square. Okay, this is the equation for principal stresses. So we will substitute here. Fx is 5, Fy is 0 divided by 2 plus half of plus or minus. So Fx is 5 minus 0 square plus 4 into tau v is 0.741 square. Okay, so therefore we will get two answers here. So I got, so we are talking about, so Fx is 5, Fy is 0 divided by 2 plus or minus half of square root of Fx is 5 minus 0 square plus 4 tau v is 0.741 square. So we got it as 5.1. So that is F1 is 5.1 Newton per mm square and F2 is minus 0.107 Newton per mm square. So it indicates, so this is compression, this is tension. So compressive principal stresses is 5.1 and the tensile constant stress is minus 0.107 Newton per mm square. So these are regarding the getting the principal stresses developed in the concrete. Okay, so this is regarding today's session. Okay, thank you.